Welcome to lab. Today's lab is going to be an actually very simple lab about Ohm's Law. The problem is I have to lecture on Ohm's Law first. So we'll start with a little lecture on Ohm's Law, and then we'll get to the lab. So first, what is Ohm's Law? Ohm's Law is the most basic of circuit rules we use to help us understand how electric circuits work. So here I have an example showing a circuit and how we draw it, and then we'll talk about what things mean. So here is the real case. You have a battery. A battery is a battery of cells. So it contains multiple voltaic cells, which are, well, I'll talk about it later. But what it does is it gives energy to charge. But we've just been learning about potential energy per unit charge. What do we call the potential energy per unit charge?
Wasn't that voltage?
That was voltage, yes. So it gives energy to charge, meaning that it gives the charge a certain voltage. And so the battery terminals have a certain voltage difference across them. And then we have the headlight, which is taking energy from the charge and converting that energy from potential energy per unit charge into energy in the form of mostly heat. About 95% of the energy is going into heating things up, and about 5% is going into light that we see. So lights are really inefficient. Lights such as we have here are more in the ballpark of 30 to 35% of the energy goes into light. That's still pretty bad, but it's like 6-7 times better than it is with a light bulb like we have in a headlight. So this is real, and this is how we draw it, how we represent it. So the first thing is, how do you write a battery? And you will see, even with this picture, the picture is wrong. A single voltaic cell is like this. That's a cell. The long side is always the positive, the short side is the negative. And these cells run by chemical reactions that generally produce somewhere in the ballpark of 1 to 1.5 volts. So if you have, like in this, it has 4 AAA cells. Each one of these is a single voltaic cell. And if you take it out and look at it carefully, it will say somewhere what the voltage is. It says alkaline. It's all in Chinese for the most part. I don't see where it says the voltage, but then again, I'm old and I can't see these fine details. Oh, there it is. 1.5 volts. So this voltaic cell is producing 1.5 volts, which is convenient because that says I should use a 1.5 volt cell. Some of them are like 1.2 volts. There is a difference in the different types of cells you buy. So these are cells. They're not batteries. What makes a battery is when you put a bunch of cells together. I have 4 cells together. Those 4 cells together, that's a battery. Why do I say battery? Y'all know who Eddie Murphy is?
Yes.
When I was in college, he had this album that was called Delirious. And in it, he has a very funny routine about cars talking to you. And it ends with, "Say man, someone stole your battery." And ever since then, I've said battery and battery interchangeably. So this is a battery because it's a collection of cells together. And something that makes people really annoyed is if you take something like a 9-volt battery. It's a battery because, it's not 1.5 volts, right? The cells have been like 1.5 volts. If you take that 9-volt battery apart, what do you find inside? You find a bunch of cells. It's just encased in a standard form. Now I say that, I'm sure there are some that are not individual cells that you see. But these days, like you buy the little motorcycle battery that's like this big, you take it apart and you see it's just packed full of AAA cells. or maybe it's double A's, but it's packed full of standard cells. It's not something special. It's just packaging. So the truth is, you could probably save a lot of money by going and buying a motorcycle battery, breaking it open, and then using the cells that are inside. Except for they might be soldered in place. You might have to desolder. So that's a cell. Now, if that's a cell, how do we draw a battery? The answer is a battery is more than one cell. And so a battery, I'm going to change the color just so, you know, battery in blue. A battery, I'm drawing mine with 3. 2 or 3, either one is correct for a battery. So there is a technical difference in the symbol for a battery versus a cell. So in this diagram, what is this right here?
Cell.
It's a cell. And it has plus and minus marked, but you don't need to have it marked because you know the long side is the positive, the short side is the negative. Then we have this headlight, and inside that headlight, what you have is a wire that is getting hot and taking energy from the charge. And so we call that a resistor because it's resisting charge flowing through it. It's resisting, it takes energy to force charge through it. That's how we get the name resistor, and we draw a resistor like this. Now for your lab today, that's as complicated as your circuit's going to get. You'll have a resistor. Well, for your scientific method test, you'll have 2 resistors. And a power supply. And we're going to draw our power supply as if it is a battery. It's not really a battery. It's a whole different ball game. It's not chemical reactions. Now, enter Georg Ohm. I just like to say his first name. Georg Ohm noticed that when he put a battery across different materials, the amount of electricity that flowed through the materials varied depending on the material. And so he came up with a relationship to relate the rate at which charge was flowing through the material, the resistor properties, and your power supply. So I need to talk about, come on, next slide. I need to talk about current before I get there. Now, in class yesterday, I introduced current ever so briefly. Remember, right at the outset, current, Krista and I were talking this through. Current is the rate at which the charge passes through a material. And so current is defined, the symbol I is the symbol for current, right there. And it's defined as, and once again, Krista and I think we're talking about this too. I keep saying Krista, it's Claudia. Sorry. Krista, I mean Claudia. It's that simple. The current is the rate at which charge is passing by. And so the units are going to be unit of charge, coulombs, divided by unit of time, seconds. And I would like to leave it at that, but I can't. Because Ben Franklin, that great physicist Ben Franklin, we talked about him before. I get a sneeze, I'm sorry.
Oh, there we go.
Yeah, hopefully that's all. Ben Franklin just arbitrarily decided, let's call whatever is on the amber, or Greek word electron, a negative charge. And so it turns out electrons have a negative charge. We're down with that. But as we've learned about conductors and insulators, it's electrons that move. So negative charge is what's moving. So if I have a wire and I have current going to the right, that means that I have, in theory, a positive charge going to the right. But the positive charges are contained in the nuclei of the atoms, and those are not moving. So there is no positive charge going to the right. So what is really happening if the current is going to the right? Electrons are moving to the left. And so this causes a divide between physicists and engineering technologist, because when I taught at PHYS, the engineering technology teacher taught a circuits class. I taught a circuits class. I taught conventional current flow, which is the current is flowing the direction of this mythical positive charge. And he said, that's ridiculous. It's a mythical positive charge. It makes no sense. And so he taught them electron current flow. So he taught them that current flows the direction the electrons do. All Ben Franklin's fault. If Ben had said, whatever's on the amber I'm going to call positive, then we'd say no problem. We have units of 1.602 moving this direction, so the current's moving that direction. Now, with physicists, we're happy. We just say Q is moving this direction, and we're good with it. And if it's a negative electron, we know the negative sign reverses the direction. But it's important to have that understanding, because at some point you might think about, but wait, electrons are moving, current goes this way, what are electrons doing? While we're on this, somebody brought up in class yesterday, at the end of class after it was over, we didn't cover some things. Are we going to cover this and that? Drift velocities we're not going to cover. It was explained pretty well by Andy when she was summarizing in the Prusol. When you have a wire carrying current, the electrons are moving quite slowly, on the order of centimeters per second. But the current flows at nearly the speed of light, because the current is caused by, well, at this point we'll say a chain reaction. The real truth is, if I have a metal wire, here's a metal wire, well, all of these are connected to something at the end. This wire, if I have a current flowing through it, here's what really happens. An electromagnetic wave flows outside of the wire, and it drags electrons through the wire because it's creating an electric field. And if you have an electric field, it's going to put a force on the charge. And so the electric field outside is pulling the charge. The signal travels at the speed of light in whatever the insulation is. And so the speed of light in polyurethane is about 2/3 the speed of light in vacuum. So that's how fast electrical signals go through most insulated wires. If you have uninsulated wires, then it goes to the speed of light, because it's going actually on the outside and dragging electrons inside. Okay, back to the topic, current. What's the unit that we use for current? Okay, amps. Coulombs per second is what you get from that equation, and a coulomb per second is an amp. And as of 2019, we went from the amp being the base unit back to the coulomb being the base unit, which makes more sense to me. Because electrons come in discrete units of charge. That is the base unit, and then the ampere is defined as a coulomb per second. It used to be that the ampere was defined as the amount of current necessary with two very long wires that are separated by 1 meter to make a force of 2 pi times 10⁻⁷ newtons per meter between them. Something that in theory can be tested everywhere, in practice is kind of hard to test. So we're not talking about the drift velocity. You'll notice here it has the electric field and current stuff, but we're just not going to talk about that. So we get to Georg Ohm. He came up with this law, I equals V over R. Ohm's Law. Now that can be written 3 ways. In fact, when I was in graduate school, I had a friend who had been an electrician in the military, and they taught him you can do anything in circuits if you know Ohm's 3 laws. So the first one, V equals IR. The second one, I equals V over R. The third one, who can tell me what the third Ohm's law is?
V over R.
Whew.
So smart.
Yeah, it made me wonder exactly how smart you had to be to do circuits if you can't recognize those are the same law. So this is the basic thing that helps us identify how charge moves as a result of us giving the charge energy. Remember, voltage is potential energy per charge. Current is the rate at which it flows. Now, with this law, there are some important things. when I draw a circuit, what does circuit mean?
Circuit means a circle.
It means it comes back on itself. A circuit has to be a closed loop. It doesn't have to be a circular loop, but it has to be closed. It has to come back to the starting point. So anytime we're talking about electrical circuits, we have to have a path that comes back to the starting point. So in this picture, the cell on the left is the starting point, and if you follow a wire either direction, you get back to that starting point again. Thus, it is a circuit. So with this circuit, current flows. Current is charge, right, that is passing through. And so that charge, anything that flows out of here, has to keep going through that circuit until it gets back to the starting point. So in this case, there's no paths where the current could go a different direction. And so the current has to be the same everywhere in that circuit because it only has one loop. We'll learn if I have multiple loops, well, then the current can split off. But this current has to be the same everywhere. Now, when we use Ohm's Law is specific to a resistor, and what this equation really says is the voltage drop across the resistor. Remember, voltage, that's the energy per charge. So the voltage drop is how much the potential energy drops per charge, or how much energy you gave away per charge through that resistor. So the voltage from that equation is the difference between the voltage on the side the current went in. You notice I put a plus sign there. I did that based on the direction of the current arrow. If the current was coming from the left going across the top, then it's got to come down. And so the tail end of the current arrow is the positive for Ohm's Law. The arrowhead is the negative for Ohm's Law because it's a voltage drop as the current goes through. And so this is saying the current through the resistor relates to the voltage drop across the resistor by that value R, the resistance.
So if the resistor were on the other side, it would be different?
If the resistor was on the other side, I'm going to draw the picture. If we had, that's what you mean, right?
I guess, sure.
So which side is positive for my cell?
The long side.
The long side, so that's this one. Current, because current is a mythical positive charge traveling, positive charge would be repelled from the positive side. Agreed?
Yes.
So that means I'm going to have my mythical positive charge going away like this. So my current is going out of the positive. And then it comes around the loop. And so my current goes like that. And then following our rule, the tail side is the positive, the head side is the negative.
Okay, so it doesn't matter which side it is so long as the flow is...
The energy is dropping as the current goes through the resistor.
Right.
And so the positive side is the side that entered, the negative side is the side that exited.
Always.
Always. Okay. Now, Georg Ohm noticed this. It turns out this is not true for every single material known to man. It's true for a lot of materials, but not for all materials. So, I thought I had, this slide was, the next one is what I thought I had. Here's an example of something that is a superconductor. In this region here, it's a normal material, so that follows Ohm's law. But in this region here, a superconductor is a material that, if you get it cold enough, it suddenly has virtually zero resistance. And so no matter what the current is, you have no voltage drop. Think about that for a minute and how useful it could be. We like to have things like, electric motors. As we'll see, electric motors require us to take a bunch of wire, wrap it in a loop, and then make current flow through it. But if that wire has resistance, which all of our wires do, then according to Ohm's law, it's going to take energy away just to make the current go through the wire. But if we could make that loop out of the superconductor, then we wouldn't have any loss of energy to make the current go through the wire, which would be beneficial for two reasons. Number one is energy, less energy used. Number two is heat, because when you're losing that energy, it's going into making stuff hot. And so you probably have noticed your computer gets really hot because you're using a lot of electricity in that little CPU, the central processing unit, as it does calculations. And so you have to cool it. Well, if you had superconductors, you would have a lot less heat loss, a lot less energy usage, and a lot less cooling you would need. Okay, back to this. Measuring voltage, measuring the energy per unit charge. Because voltage is always between 2 points, it's a reference from this point to this point. When you measure voltage, you'll always have to have your meter, so you have one connector on one side of the resistor, the other connector on the other side of the resistor, and then you're measuring the potential energy per charge, the voltage difference across the resistor. Now we call this kind of connection parallel. Is that how I spell parallel? Probably not. Yeah. Okay, it's parallel because you have the top connected to the top, the bottom connected to the bottom. So the top of the voltmeter is here, the top of the resistor there, those connected together. Bottom of the resistor connected to the bottom of the voltmeter. Of course, nothing in life is perfect. I talked about before with our single loop, the current had no choice but to follow that loop. But now if you look at this, that blue current arrow does have a choice. When it gets here, the current could go here or it could go there. And so in reality, if this voltmeter has a very low resistance, that means it's not going to take much energy for charge to go through it. Then I'll have a lot of current that goes through the voltmeter. If it has a really high resistance, then it'll be a very small amount of current that goes through it because it's harder for the charge to go through. What do we want our voltmeter to do? Do we want our voltmeter to change the fundamental behavior of the circuit? No. So that means we don't want any current going through the voltmeter. So we make these voltmeters so the resistance of the voltmeter is very large. Now we haven't talked about the units yet of resistance. So I'm going to go, that's not backward, go backward here using the third form of Ohm's Law. You can calculate what the units are. The units for resistance must be volts. A volt is a joule per coulomb divided by amperes, and amperes a coulomb per second. So that's equal to a joule times a second per coulomb squared. That's a C. And we never, ever, ever write this because we define that as an ohm, named for Georg Ohm, who made Ohm's Law, and we use the Greek capital omega as the symbol for resistance. So omega is our unit for resistance, and it's equal to volts per amps. So a typical resistor might have a resistance of what we're going to be using in lab today, are resistances between about 500 ohms and 1500 ohms. We like to use prefixes, so 1.5 kilo ohms. The voltmeter might have a resistor that is greater than a mega ohm, greater than 1,000,000 ohms. You know, if your ohm or your voltmeter has a resistance that's like 1,000 times bigger than the resistance you connect it to, it's 1,000 times harder for charge to go through the voltmeter. You're not going to have anything go through it effectively. And that's the goal. No one's asked any questions. I've gone through a lot of stuff actually already. Any questions about what I've gone over?
I'm really confused about the flow with the pipe and the mythical proton, the mythical positive charge. Can we go back to that slide? Right there.
So
I don't understand what you're saying about like how this is how we think about it, and there's like a different way to think about it, and this isn't actually what's happening.
okay, here's reality.
Okay.
Reality, if current is going to the right, you have negative charges going to the left.
Okay.
But as we've learned, negative to the left, just like when we were first semester talking about vectors. If I have a vector that's negative 5 meters east, that's really 5 meters to the west. And that's what we have, for physicists, we're happy with that. If I have a current going this way, I know that really means negative charges going that way.
Okay. So for our class, the current is always the direction of the positive charge, but the positive charge isn't really happening. It's just
Correct.
like negative is opposite.
Right, that's right.
Okay.
And you'll see with the software we're using in lab today, it will show you both views of the flow of charge. The resistance of a material depends on what it's made of. And so this thing here, rho, that's called the resistivity. So if I make a resistor out of a different material, it'll have a different resistivity and have a different value. It also depends on the geometry, the shape of your resistor. So it's the resistivity times the length divided by the cross-sectional area. Anyone who's worked with electrical wiring, which is probably not many of you, knows that you have wire of different gauges. You have some wire that's pretty thick and some that's very, very thin. Why? The answer comes down to this. If you have a thick wire, what's that going to do to the resistance? It's going to reduce it.
Yeah.
So if you are wiring for the circuits in a building like this is wired so they can handle more current than you can have at home. A typical household circuit, I think, is supposed to handle 15 amps of current. These are probably more like 30 amps. And so if you're going to have more current, then that means more charge per second passing through. And with resistance, the resistance multiplied by that current is going to give you the voltage drop, which is how much energy you're losing per charge. How much energy is going into heating. So if you're going to have more current flowing, you need to have less resistance or you're going to start a fire. So that's why they have bigger wires so you don't start fires. So if you have something that doesn't require much current, you can have a very small wire. But if it requires a lot of current, you're going to have a bigger wire so it doesn't get too hot.
So then, rho would depend on the specific material. You have kind of like the coefficient for friction.
Yes.
Okay.
There's one more thing that I don't think I have a slide for. The resistivity also depends on temperature. So when you change the temperature of a material, its resistance will also change. And so you have something like rho equals rho 0 times 1 plus alpha t, where alpha is something to characterize how it's going to change with temperature changes. And that's actually really important for things like light bulbs. The resistance of the filament of a light bulb when it's cold is very different than the resistance of that same filament when it's hot, because it's a very big temperature change. I have to define AC versus DC. Right now, everything we're doing is what we call DC, direct current. Direct current means that the current is always flowing the same direction. And on meters, you indicate direct current with something like that, a solid line with a dashed line above it. AC, actually, I think we do it like that. AC is alternating current, which means that the current sometimes goes one direction, sometimes it goes the other direction. It goes back and forth. So the power coming out of plugs up here, or like this plug here, that's AC, which means that electrons come out, electrons go back in, out, in, out, in. The net motion of the electrons is zero. They don't go anywhere. But they move back and forth, and you transfer energy by the chain reaction of making electrons further down move back and forth. So all we're doing today is working with DC. I want to introduce it now so you know the difference. Now for how a battery really works. So here is a lead acid battery, a typical car battery. You guys probably know car batteries are heavy, right? They're heavy because they're based on lead. Lead is reasonably dense. Now if it was based on gold, it'd be much heavier, but that would be silly.
And expensive.
So what you have is sulfuric acid and a lead plate and a lead oxide plate. And just a note, you don't want to mess around with a bad battery with any clothes that you want to keep. You might have noticed the pants I was wearing last semester that had some holes. That was the result of changing a battery that was bad. And it leaked battery acid on my clothes, and that's what put the holes in them. Those clothes have now been retired. So the way this works is you have chemical reactions that occur at the two different types of metals. So the lead oxide with sulfuric acid is going to have an electron that it absorbs to produce lead sulfate and water. So it's going to be trying to pull electrons in at the lead oxide terminal. At the lead terminal, you have the sulfuric acid reacts with the lead to produce, again, lead sulfate and free hydrogen ions and free electrons. And so the lead terminal is giving up electrons. So what happens with this when you put the whole thing together, since you have fluid that can freely flow between these plates, is that you will have a reaction that goes until you reach equilibrium, where you have the voltage difference on one side compared to the other is sufficient to stop those reactions. And so the battery should have, for each single cell, about 1.5 volts. But as soon as you start to use the battery, then you start to put a resistor across the top so electrons can flow across. Now, I drew my arrow the direction of mythical positive charge. If you're going to talk about the actual flow of electrons, the electrons themselves are going to go from the negative terminal to the positive terminal. But as soon as we have electrons flowing, then my equilibrium is broken. The voltage is going to drop when you use the battery. Why is it dropping? Because it's no longer in the, I always think of this as the saturated state. It's probably not an appropriate term. But now you're not in equilibrium. Now you have the charge on the positive plate is a little less positive. The one on the negative is a little less negative. And so the reaction kicks in. And then the reaction tries to raise the voltage back. So when you use a battery, as soon as you use it, the terminal voltage is going to drop. If the battery's good, it shouldn't drop very much. If the battery's bad, it drops a lot. So how you test a battery, you don't test it by measuring the terminal voltage of an unused battery, because the terminal voltage should always be the same unless it's completely broken. But if you put a load on it, if the chemical reaction can't go quickly, the voltage drops a lot. That's a bad battery. And so when you put a load on it, you measure how much the voltage drops. When you put the load on, that tells you about the battery state. So battery testers are always going to put a load on the battery and measure how much the voltage drops when you put a load on it. Now, are you guys familiar with battery testers? Okay, David gave a very strong affirmative nod. What kind are you familiar with?
Trying to remember what it was.
Well, my favorite, I don't know if they still do this with some of them or not. They used to make batteries where you press on this little thing on this side, press this little thing on this side, and it has a little strip that changes color to tell you if it's good or not.
I remember those.
How does that work? I'm sure Aaliyah was correct. I couldn't hear what she said, but you know, when people have the courage to talk, I give them credit.
Good job.
So what you're doing in that case is you have a resistor that is like, well, resistor, so I better. a resistor like this that's not making contact to the two ends because you don't want to drain your battery. But when you press on the two little ends, you push it down so you make it make contact. And when you make it make contact, now we have a resistor connected across the battery. What's going to happen? Current's going to flow. And as that current flows, we're going to have energy loss. That is, energy is going to go into heating up this resistor. And so how they actually make this thing work is on top of the resistor, they put a polymer that is designed so it will change colors with temperature. You guys ever heard of a mood ring? A mood ring is a polymer that changes color with temperature. They use the same thing as a mood ring. And so when you have current going through there, that little polymer gets warmer, and if it gets really warm, it changes to green and tells you good. If it doesn't get warm enough, it doesn't change to green and it's not good. Yeah. No. Can you use a wrench? Yeah. You're not going to get an accurate reading of any kind. And if you use a car battery, you can grab both posts, it will do nothing to you. But if you put a wrench across those two posts, it will weld it to the battery.
I did that. I'm not even.
I do believe you.
I was trying to unscrew it and it like touched it and it started sparking. My car blew up. Oh my God.
I was going to make a statement and I held it in. Anyhow, moving forward, one of our last stops before we get going is actually what your scientific method thing is about today. About resistors connected in series or parallel, or batteries connected in series or parallel. So I already talked about what parallel meant. This picture on the bottom is 4 resistors connected in parallel. They're connected in parallel because all the tops are connected together. And similarly, all the bottoms are connected together. Any place where 2 or more wires come together, we call a node. So this is a node, and this is a node. So this here is parallel. Now when you have the resistors in parallel, since all of the tops are at one node, all the bottoms are a different node, the energy difference between those two nodes has to be the same regardless of which resistor you look at. So each resistor has the same voltage. But the current is the rate at which charge goes through. If one of those resistors is a low resistance, that means that it's easy for charge to go through, it doesn't cost much energy. Charge will preferentially go through the low resistor one. So current is potentially different for the different resistors. And make sure we know that's for parallel. So if I put the resistors in parallel, they all have to have the same voltage, the same energy drop per charge. But the current, the amount of charge flowing through each resistor per second varies depending on the resistance values. Series, on the other hand, so I'm going to change to green for series. This here is series. Series, any current that goes through one has to go through the next, has to go through the next, has to go through the next, and comes out. Because there's no other pathway. Series, you have them connected in serial, one right after the other. And so in series, you have the same current through each resistor. But of course, because Ohm's law is V equals IR, then you're going to have different voltages for each resistor. VOLTAGES. So in something like, once again, let me pull the back off of this. In something like this, I have a bunch of batteries connected in here. And so they're either connected in series or parallel. How can I tell? Well, if I pop them out, I might be able to see how these things are connected. And the way they're connected is, there's a connection going like from here to here, and then here to here, and here to here. Actually, no, they're in series. So what's actually, I probably did backwards, yes. It's here to here, here to here, and here to here.
Oh, okay.
So this here, now with the batteries, these are nice in that it's got a gold on the positive side. The side that sticks out is the positive side. The side that's flat is the negative side. And so these go positive to negative to positive to negative. So that if you add up the voltages, they add up. So you're getting, instead of 1.5 volts here, you get 1.5 plus 1.5 plus 1.5 plus 1.5, 6 volts. So this is a 6-volt battery made out of 4 AAA cells. And how are they connected in this example? In series. Why are they connected in series?
The alternate resistors, right?
Okay, I determined it because of the order of how they're aligned. But the purpose was to get a higher voltage. Now, in some things, you will have the batteries connected in parallel. In my Roku remote, they're connected in parallel. Why would you connect them in parallel? I don't know. Is that your answer?
Yeah.
Final answer?
Final answer.
Not going to call a friend? You would put them in parallel if you want more current. So in my Roku, I have 2 1.5 volt cells in parallel. It's taking in 1.5 volts, but it's going to use more current than you can produce with one cell alone. Yeah.
So in series, you're increasing the voltage, but in parallel, you're increasing the current.
With batteries, yes, or with cells. Yeah. Cells or batteries. That's correct.
As opposed to what?
Okay, as opposed to with resistors.
Oh, okay.
With resistors, we often will calculate an equivalent circuit. So we'll say, here's an example with a total of 3 resistors in that circuit. I'm going to erase my box. Just that one there has 3 resistors. If I want to calculate how much my total resistance is, I say, well, the battery has a certain voltage, and there's a certain current that's drawn through those resistors according to Ohm's law. And so each one of these resistors, what arrangement is this? Is this series or parallel?
Series.
Okay, so this is series. So if it's series, I have the same current through each one. So that means the voltage through resistor 1 is equal to I times resistance 1. Voltage through resistor 2 is I times resistance 2. And the voltage through resistor 3 is I times resistance 3. Does that make sense? That's just applying Ohm's law to each one of the resistors. Now, if I look at the total voltage from here to here, it went down V1, V2, V3. And so my V total is equal to V1 plus V2 plus V3. Each one of these had the same current, so I'm going to factor that out. So that's current multiplied by I times R1, so R1, plus I times R2, plus I times R3. And so my total voltage is current times R1 plus R2 plus R3. So what's my equivalent resistance? Well, according to Ohm's law, V over I is equal to the resistance. So if I just take this final equation, divide both everything by I, Then I have V total over I equals R1 plus R2 plus R3. And that there is my what we call equivalent resistance. So if I put resistors in series, the total resistance is just the sum of the resistors. That makes logical sense, doesn't it? It's like, if I have 3 bags of sand that I pour into a tub, the total amount of sand is, 3 bags, adding them up. But it's not the same if I were to do them in parallel. So, I don't have a good page to do this on for parallel. I filled this whole thing up with the series. If you do them in parallel, what's the same for all of the resistors when they're in parallel? The current. No. That was for series. They all have the tops connected together. They all have the bonds connected together, so they have the same energy per charge. What do we call that? Voltage. They all have the same voltage. And so in this case, I'm going to calculate the current through each one. So current 1 is equal to that voltage over R1. Current 2 is that same voltage over R2. Current 3 is that same voltage. It's going so slow. Same voltage over R3. And remember, current is just charge per second. So any current that goes out of my battery has to go through one of the available pathways. So it has to either go here or here or here. And so my total current is I1 plus I2 plus I3. And doing like I did before, if I substitute I1 is V over R1, I2 is V over R2, I3 is V over R3, I've run out of space, but what I'm going to have, I can factor out the I, or the V, and I have I total is equal to V times parentheses 1 over R1 plus 1 over R2 plus 1 over R3. I'm actually going to write this at the top of the screen because I have a little more real estate. It's going to come up. I trust it. So it's almost there. Once again, the definition of resistance was V over I. If I divide both sides by V, I'll have 1 over resistance. So if I divide both sides by V, that's equal 1 over the resistance equivalent. So that's R equivalent. It almost looks like EQ. So if you have resistors in parallel, 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. What does this mean in practice? In practice, it means that the total resistance in parallel is smaller than your smallest resistor you started with. When you add resistors in parallel, you get a smaller resistance. Why? Well, if you think about the logic of it, the resistance is the energy per charge necessary to force the charge through. But if you have multiple pathways, it's going to be easier for the charge to get through. It's like the water pipe analogy. The water pipe analogy, resistance is a measurement inversely proportional to the diameter of a pipe. A small diameter pipe is a large resistance. Large diameter pipe is a small resistance because water goes easily through a large pipe, not so easy through a small pipe. If you have 3 pipes set up, the water can go through each of those 3 pipes. It's like having a single pipe with a bigger area. And that's what's going on here. Having the resistors in parallel is like having one bigger resistor. That is by bigger area, and the resistance was inversely proportional to the area. Because this is what you're doing for your scientific method test, I want to make sure. Do we have questions about adding resistors in series versus parallel? Okay, simple questions. If I take two resistors and I put them in series, do I get a bigger or smaller or the same resistance? Bigger. When you put them in parallel, it's the sum of the individual ones. Or series. Now I have to go back. Yes, if I put them in series, it's the sum of the individual resistors. What about if I put them in parallel?
Smaller.
It's smaller. And in fact, it's smaller than the smallest one you started with.
Oh, okay, you just said
Parallel, they're smaller.
series is the resistance of the sum.
Yes. Parallel is the 1 over R equivalent is the sum of the 1 over R's. All right. We won't worry about simplifying today. We'll worry about that in class tomorrow. I do want to get to electrical safety before we start the lab. You are in absolutely zero danger unless you do something silly like grab the prongs here, But I want to make sure you understand things about electrical safety because, some of the things I do in class are not very safe. And I have to make sure I don't kill me. So, first things first. In class yesterday, we talked about the body running on electricity and how with the heart, when the heart muscle depolarizes, makes the muscle contract. And that happens naturally, but you can make it happen artificially by using a defibrillator, which puts a really large voltage across the heart to make it depolarize, even though it internally wasn't going to do it. So we can do the same thing with other muscles. So here's my hand. If I touch something and it passes current through my body, it will make the muscles contract. And so if I have the wire like this and the muscles contract, what am I going to do to the wire? Grab it. And then I go, ah. That's not good, right? So if there is some really, really bizarre case where you just have to touch something to know if it's hot or not, don't grab it like this. Touch it with the back of your hand. And just to be safe, put your other hand in your pocket, okay? So you touch it with the back of your hand, then if it's hot, what do? You face palm, right? It's really clear. Face palm, it was hot. No face palm, it wasn't. As opposed to grab and hold. Now, why did I say put one hand in the pocket? Does anybody know?
Isn't that like a grounding mechanism?
It's not grounding, but it's a way to keep you from dying. Or make you less likely to die.
Oh, it's important to your body.
So talk about things that could cause you to die with electricity. We're not going to open this up to the whole gamut. Okay, I'm going to start with something less. If I have electricity going across my chest, that can cause my chest, all it takes is about 1 milliamp. 1 milliamp? I think it's about 10 milliamps for you to feel. I have it on coming up. About 10 milliamps for you to feel a tingle. No, it's 1 milliamp to feel a tingle, 10 milliamps for the muscle to start contracting involuntarily, like you have no control. If you've ever gone to the chiropractor and they put you on their little stems thing, they just put wires on your back and they run alternating voltage across them and the muscles contract, right? It's just like putting a defibrillator on your muscles. I think it's a wonderful thing. I think we should all have those. We should just go to bed with them and let ourselves work out while we're sleeping. It's my idea of the way to work out. So, if you have a current going across your chest and it's high enough to make the muscles involuntarily contract, well, then you have a real problem. Because when your intercostal muscles contract, you push air out of your lungs. So you go, but then if they don't release, you don't allow atmosphere to push air back into your lungs. And so you can actually suffocate if you have a prolonged period of time with current prolonged period being measured in a couple of minutes. Chest going across the chest. Current going across the chest. I don't know how I mess up words, but it happened. So that's a bad way to go. So if you were to grab something and have that current going through you, and it went from this hand to this hand, it'd be going across the chest, and you would potentially have that suffocation risk. Then your next risk comes from the heart itself. You get to about 70 milliamps across the heart, and it will cause the heart to depolarize without you telling it to. And so that can cause fibrillations. Bad. So the next danger is getting up to about 70 milliamps across the heart. So the first one I talked about was just across the chest, making those intercostals tighten up. Less current required for that. Then across the heart, causing you to have fibrillations. But it gets better. If you get up to about 1 amp across the heart, what do you suppose the heart's going to do? The whole thing is going to depolarize. Assuming that current stops, then hopefully it'll repolarize and keep going. That's what we're doing when we put the defibrillator on somebody. We're putting enough current across that heart to make the whole thing just go, and then we release the current, and hopefully it just says, hey, here we go, and goes back to running. So it's actually safer to have more current across the heart. So I was telling somebody about a student a couple years ago who, during a physics project, made a foolish decision and tested both sides of the capacitor charged to a little over 400 volts. That's enough to just stop his heart completely. It didn't kill him. If it had been less, it could have killed him. But it was enough to not kill him. Good times, right? I would have been devastated.
What did happen?
Huh?
What did happen?
What did happen? I think he fell down and then he woke up. I wasn't there. They were working at night. But it scared me when he told me. He wasn't as scared as I was because, it survived. So, what's the last way electricity can kill you? I talked about making you suffocate. I talked about putting you in heart fibrillations. What do you suppose the last way is? Like, say you get struck by lightning, how would that kill you?
Isn't it just?
It burns. It burns you. One of our family friends was changing sprinkler pipe, and there was a gopher in the pipe. So he did what we all do, tip it up like this, get the gopher out, and he hit a high power line with the aluminum pipe. And it killed him. And they said you could see on his hands where he had big burns going in. You could see on his feet where he had big burns coming out. If you sectioned the body, you would have seen big burns through his body. Oh, there's a couple more things I should talk about. If you watch something like Rambo, they torture John Rambo by tying him to a bed frame, and then they whip him, and then they take a car battery and they shock him, right? I just told you earlier, you can grab the two posts on the car battery and it's not going to harm you. So how can that work? The answer is it can work. Does anybody know?
Isn't it because he struck the metal bed?
Not just that.
Not just okay.
Think about how you test a 9-volt battery. How do we all test 9-volt batteries? You stick it on your tongue. What happens if you put your finger on the 9-volt battery?
Nothing.
Nothing. But you put it on your tongue, and what does it do?
It gives you a little shock.
It sizzles. It sizzles. Why?
Because there's a lubricant there.
Not a lubricant. The moisture makes it so you have a much lower resistance. And so there's a lot more current flowing, and hence you're depositing a lot more energy. So we have the same idea here. Your body has this protective layer, skin. And that skin has a pretty high resistance. It's measured in somewhere between, if it's wet and nice and lubricated skin, it lowers the resistance of the water. Lowers the resistance across the skin, so it might be just a little over a kiloohm. If it's dry skin, it'll be maybe 100 kiloohms or so. So wet skin versus dry skin, very big difference in resistance. But still, think about the numbers I quoted. What kind of current do we need for you to even feel it? Where in the world did I put my pen? There it is. What kind of current do you need to even feel it? Around 1 milliamp. 1 milliamp. So if I have a 12-volt battery and I want to get 1 milliamp, how much resistance do I have to have for 1 milliamp? What does milli mean? 1,000th, okay? So Ohm's law says R equals V over I equals 12 volts over 1 milliamp equals 12 kilo ohms. Kilo means 1,000, milli was 1,000th, so the units work. So if the resistance is less than 12 kilo ohms, you could feel it. If it's less than 1 kilo ohm, 1.2 kilo ohms, my rough number, it can cause your muscles to involuntarily contract. So the key was, yeah, they put water on Rambo, but they also flayed his skin, right? They cut him up. You cut him up, you go through the skin. Now you have direct contact and the resistance inside your body really, really low. So once you get inside the skin, you could easily torture somebody with 12 volts. Outside the skin, it's not going to happen unless you have a really special case. So you could, and of course, keep in mind, I am not recommending torture at all, but it is a theoretical possibility if you use a car battery and you cut the person and you put the probes in the cuts, or you have water so they can, conduct to it. Okay, so I do have some slides on here about threshold for sensation. I was saying about 1 milliamp. If you look at this graph for DC, it's actually more like 3 milliamps for you to feel it. And it comes down to about 1 milliamp if you get to a frequency of about, 60 hertz. What's 60 hertz? That's like, hey, we can feel that better than we can feel anything else. And it will cause your muscles to contract pretty well compared to any other frequency. So 60 hertz is a pretty bad frequency to choose. It's just about the one that we're most vulnerable to. And so you can see, once again, I was saying the threshold for the muscles to contract was about 10. This graph would say about 18 for DC and about 14 for AC. Notice what happens when you get to really high frequencies. Really high frequencies, you can withstand a lot more current because it actually doesn't penetrate. And this here is just a general rule of thumb for where death occurs from, I said, around 60 to 70 milliamps across the heart. This is rounding that to 100 milliamps up to 200 milliamps. That's the range where the heart's going to go into fibrillations. Above that, you stop the heart and it's safer. So it doesn't make sense that more current can be safer than that, but it is. And here's some good rules of thumb for resistance of different things. Wet skin about 1 kilo ohms, which means the car battery, if you had wet skin, in theory, could maybe shock you. Remember, you do have skin on both hands, so it's really 2 kilo ohms across 2 layers of skin. Dry skin, yeah, not gonna touch you. And then body resistance, if you cut it open, really low resistance, it's definitely going to cause some damage. Final thing before we start is household wiring. So we have these 3-prong outlets. Now, back in the day, like my wife's grandmother's house, which thankfully we sold a few years back, they just ran one electric wire through a house. One electric wire. That one wire is the one we call the hot wire. But circuits always have to go in a loop, right? One wire, you can't have a circuit. Well, what do? You have water pipes in the house. Those water pipes are going into the ground. And so they just connect the other side of the circuit to the water pipe. Voila! It goes around the loop from ground to your power supply, back to the water pipe, back to the ground. Yeah.
Hold up. That's really interesting because when I was in Zambia, our sink would always shock me. Like, if I touched it a certain way, it would shock me.
You might have been in a situation like that. I don't know, but so that's a bad way. That's a bad way of doing it because if you have it connected to the sink and the sink is not well connected to the earth, and you touch it, you get shocked. So then they got smarter and they put in 2 wires. So a typical household circuit, notice to me this looks like a man screaming. Typical household circuit, you have a small prong and a big prong. And the small prong is the hot wire. That's the one that's carrying the electric signal. And the big one is what we call the neutral wire, which is independently connected to the earth without going through your house's, water plumbing. That's good. So that's how houses built, 60s or so would be made. But then there are all things like, you could still, if you have a fault, like let's say your refrigerator has some wire that falls against the chassis, you can still get shocked by that. So we're going to go one step further for safety. We're going to put a 3rd wire. So houses today are always wired with 3 wires. The first 2, the hot wire and the neutral wire. And then the last one, the mouth, that's the ground. So what's the difference in ground and neutral? Different pathways to the earth. The electric circuit is always supposed to be going between the hot wire and the neutral, and then you can connect that ground wire to things that a person might touch just to give them an extra layer of safety. So that's what those things are. That's why we have 3 wires, for safety. And I kid you not, when I was teaching at PUC, they had a science day at Redwood Baptist Junior Academy. And the guy who was giving the devotional talked about how when he was a kid, he liked to take metal clothes hangers and stick them into electric sockets. He's telling this to 1st graders.
Oh.
Yeah. I'm like, oh, are you crazy? Is it safe to do that?
No.
Max says it is. If you knew what you were doing, or like Russian roulette, except for instead of 1 in 6 odds, you have, well, assuming you're using a 6-shooter. If you have a clip Russian roulette, it's pretty much always a lose. If you're sticking in one of these, if you stick it in this one, safe. If you stick it in this one, not safe. So it's a 50-50, not safe. Don't mess around with those things. Don't say, I'm going to be cavalier, it's not going to hurt me. Because if your skin is dry, you're probably going to be good. If you're a little sweaty, you're probably not going to be good. Question, Claudia Krista.
Yeah.
Sorry, I kept saying Krista.
If the power goes out, is it okay, does it make a difference if you turn off your appliances and stuff like that and then wait for it to come back on and then turn it on? Or if it comes and there's a power surge? Okay, so this is a different thing, but I will answer. It's a good thing. Let's start with simple stuff. We see here Andy has her transformer plugged into her pad, which she's apparently been running with her non-dominant hand on, or something. This transformer, when you first plug it in, it's going to have a power surge. Power surges can be bad for devices of any kind, especially electronics. So if you're using a transformer, you should always plug it in first, then plug it into your device to avoid that power surge. The same thing would be true of your devices. When the power goes out, there's 2 things that happen that can be damaging to your appliances. One is you could have a power surge. The other is you could have a brownout situation, a situation where you're under voltage. So instead of 110 volts to 120 volts, that's what the range is supposed to be, you might be at 95 volts. And a lot of appliances will be damaged if they're running at an under voltage situation. So it is safest to turn them off so you don't risk that damage. All right, let us take about a 10-minute break and then we'll get started with lab. And then in a half hour, we'll be done with lab. Oh, really? It's going to be that fast?
Oh, yeah.
I thought it was going to be hard.
Yeah.
It was
Wait, the other hanger